Good afternoon, everyone. Thank you for taking time out of your schedule to sit in on today's webinar. I'm Lee Edmonds, and I'm joined today by Phil Darlington from PTC. We'll be taking you through a short presentation and technical overview of PTC's new Creo Flow Analysis extension, our fully integrated solution for computational fluid dynamics, or CFD as it's more commonly known. We'll kick off with a brief intro to CFD and some of the features in the new FAX module. We'll then do a short review of the packaging before diving into some of the technology. Computational fluid dynamics is a branch of fluid mechanics that uses numerical analysis and data structures to solve and analyse problems that involve the flow of fluids. Applications for CFD can be found in all areas of manufacturing, and good analysis is critical in a lot of industries for ensuring optimum end product performance and quality. There are, however, a number of challenges associated with performing these types of complex analysis. Mainstream engineers tend not to be given access to the tools required to perform these analyses and often lack the skill sets required. Often, CFD requires investment in expensive third-party analysis tools and employing high-salaried analysts. It can also be very time-consuming to complete a full CFD analysis, particularly in the early stages of a product's design. This all leads to an over-reliance on expensive and often long lead time physical prototypes in order to determine if the product is fit for purpose. Creo Flow Analysis Extension brings CFD capability for the everyday engineer. It gives access to sophisticated tools so that analyses can be performed quickly and easily throughout the product development process. This in turn decreases product development costs through reducing the reliance on expensive third-party tools and physical prototypes. Time to market also decreases as less design iterations are generally required. The module will give the designer a platform to eliminate costly errors and the freedom to explore more design concepts, ultimately leading to a more efficient and higher quality end product. So why Creo Flow Analysis Extension? Well, it's easy to use. Everything's available in the same familiar Creo user interface. This gives seamless integration between the worlds of CAD and CFD. Creating analysis models is easy. There are configurable templates. The meshing is ultra efficient. And it's a one-step creation to create those solid and fluid domains. Our proprietary algorithm gives you a rapid turnaround of results so as not to hold up your design process. And most importantly, the results are highly accurate. If you're on Creo 4.0, M040 or later, you can take advantage of this add-on module immediately. It's fast, accurate, and above all, easy to use. There are 3 levels of the product to give you the right CFD capability for your role. All levels of the product will calculate internal and external flows, give you fully animated results, and offer parallel processing. The entry-level module allows us to simulate flow, heat transfer, and turbulence, and is ideal to use as an iterative tool by design engineers for quick checks throughout the design process. The Plus version adds particle, radiation, and species analyses, and allows for moving or sliding meshing. We also offer a premium package for the high-end analyst, which provides the ability to simulate cavitation, as well as bringing multi-phase, multi-component, and dynamic simulations into play. At this point, I'm going to hand over to Phil for the technical overview. Thanks, Phil.
Okay, so thank you for the introduction, and now we'll take a look at the technical section of the presentation. I've got 4 examples that I think cover most use cases that you'll encounter, and these are the examples that I would like to present to you today. The first concerns a cyclone, and this is looking at an internal analysis. So this is the flow coming into a vortex, the result of what happens inside that vortex, and then as the flow exits out. And so everything is contained within this assembly. The next example I'd like to take a look at is the reverse of this, really. This is an external analysis where we take a component such as this, a drone or a plane or maybe a car, something like that, and we want to look at the outside performance of the aero surface of that component and see how they perform in relation to the real world. The next one along is the interaction between two sets of different materials. So in this instance, it's the internal heat transfer of some electrical components. So this might be something like the inside of a computer, where you have a fan drawing the air through across the electrical components, through heat sinks, that sort of thing. So you've got the interaction between the flow of the fluid, which is effectively the air, and the electrical components, which are solid and generating heat, so they're going to have different thermal characteristics from that of the air, and also the result then of how that actually cools those components down. And the final one I want to take a look at is an assembly. So this is where we have moving components, and in this particular instance, we're going to be actually looking at a fluid. So the other three examples are looking at air and how that moves around their different experiments. This one is looking at a fluid and how that moves through a pump assembly and how the vanes in that pump assembly interact with the other components as they're actually moving. So let's take a look at the first case now. I want to do the first one. I'm actually going to do this one live. The others I've got pre-recorded to make sure that I fit within the time constraints, but the first one I'm actually going to perform live just to give you an idea of how this actually works in reality. So here is my Creo session. This works in Creo 4 MO40 or Creo 5, and I'm looking at actually Creo 5 here. So let's go and open my assembly. And the thing to note here is that CFD is another pick on the tabs like any other application that you would expect. And this is an important key aspect of what's happening here in the Creo fluid analysis extension. There are three things I think that are critical to point out. The one is ease of use, the next is that it's fast, and of course the first two become largely irrelevant unless the results are accurate, and the results that we create here are very accurate, as good as you can expect. So let's take a look at how the actual workflow works. We will go into flow analysis, and I'm going to create a new project, and these are the critical areas that we have to fulfill. When we create a CFD analysis, there are 4 key areas that we need to fulfill, and you can see here in the model tree that we get an additional CFD tab on the model tree. So the first is the physics. So when you go and buy a license of CFD, this is what you're actually buying. You're buying the maths that goes behind the analysis. So we need to fulfill the physics. We need to tell it where we're going to actually do that analysis, so the domain for that analysis. Then we need to define some boundary conditions. In the same way that if you were doing a structural analysis, you would tell it where it is held and where the loads are applied. This is a similar thing with CFD. We need to tell it the boundary conditions. And finally, once we've gone and run it, we need to examine the results. So let's go ahead and do these now. I'm going to use some of the functionality within Creo CFD product to actually go and create my fluid domain. This is an experiment that's entirely contained within this assembly, so I'm going to create a fluid domain to define the area for that experiment. So the openings are defined by these surfaces on the ends here, and when I select those, you can see that it automatically determines where the openings are, so it knows where those holes are at the ends of the assembly. That's an interesting point to note there, because when I say go and add this model to my assembly, what it also does is by virtue of the fact that we had holes on the ends of those openings, it automatically finds the fact that we need to apply boundary conditions at those openings as well. So it's already picked that up for me, so it's got the intelligence there. So this is part of the ease of use aspect. So we have the volume inside. If I turn off the CAD bodies now, what we're looking at now is the remaining volume, which defines the area that we're going to be analyzing. And if I go to the model tree, what you'll see here is that we've actually got an additional component in the model tree here now, and this is the fluid component of the experiment that I'm going to be performing. So let's go back to the CFD tab and apply some boundary conditions. Before I can do that, I need to tell it what physics that I want to employ in the calculation. So let's go and tell it that I want to look at some turbulence, and also I want to visualize the results, and to do that we go and select the streamline option there. Having done that, you'll see that when I pick on the boundary conditions this time, we actually get some additional options in the bottom half of the model tree here. And you can see by default, the boundary condition for the opening is a wall. So that's something that's solid. I don't want this to be solid. I want this to be a specified, and in this instance, I'm going to say a specified velocity. I don't know where the coordinate system is, so rather than giving it a Cartesian value, I'm going to say just flow in normal to the boundary. And what value do I want to assign to that? Well, I'm going to say that it wants to be 5 meters per second. Something I'm also going to specify here is to release the particles. Now, when you see a car in a wind tunnel, you typically see the smoke flowing over the top. This is what the particles are doing also. So I'm going to say that I want to have particles released. Now, this doesn't affect the experiment in any way. It's simply a way of visualizing the results. So at the other end, this is simply going to be exposed to the outside world. So this is just going to be atmospheric pressure in here. So I'm going to say it's a specified pressure outlet, and I'm going to say that that pressure is going to be 1 atmosphere, which is 101,325 pascals. So before we go on and run the experiment, we need to generate a mesh. If I try and run it without doing that, you'll see that it gives me the message, look, you haven't meshed your experiment. Do you want me to go ahead and do it automatically? So once again, you know, the ease of use aspect, it's actually doing this for us. But I'm going to say, no, I don't want it to do it, because I want to go and show you what happens. A couple of things when I generate the mesh. So I'm going to click on this now. 1, 2, 3, click. The first thing I want you to take note of, that's how long it took to generate the mesh. Super fast, and it's also a very high quality mesh as well. Let's just turn off the flow body here. And when I go and look at the results, because one of the results that it's gone and calculated, of course, is the mesh. So let's just go and turn on the grid for that. And we can see that what it does is it applies a standard brick size everywhere, but when it starts to intersect any detailed geometry, what it does is it subdivides the brick and subdivides until it's satisfied my initial setting for the minimum brick size. And that's set here. You can see that we can define what our maximum and minimum cell size will be, and this is relative to the size of the model. So it generates a mesh very quickly, very accurately, and very robustly. That's the important thing as well. Let's go back to my mesh again. I'm just going to turn those grid lines off, and now go ahead and actually run the experiment. So again, one of the things I want you to take note of here is the performance of our CFD solution. So when I hit run, you'll see that the simulation is already complete. It's that fast. So let's go and examine the results now. And I went and elected to turn on the flow lines in this experiment, and here they are. At the moment they're static, and the other thing about them is they're not displaying any specific parameter. So I can go and select the variable that I want to view here, and I'm going to say that I want to have a look at the pressure. This is a static view of the pressure. If I want to, I can go and animate this and perhaps change the size of those particles as well. Maybe make those steps a little larger, something like that. So we can see the flow going through here. If I want to make that line thickness a little thicker, I can go and do so. And we can see the flow going through here. But one of the things that you notice is that there's a lot of information that we're looking at the moment. So it's not that easy to go and scrutinize and drill down into a specific area of this experiment with so much going on the screen. So one of the things I can do is I can elect to go and show a section view here. So if I click on the section view, you can see into my results section, I now have this additional setting here. So I'm going to select on my section view, say that I want to look at it through the Y-plane, and let's just go and move that up so it's going through the inlet here, and go and turn on the parameter that I want to examine. And in this instance, I'm going to say that I want to look at the pressure flowing through here, and this gives us a more discrete view of the experiment and what's happening. If I want to look at it in conjunction with the streamlines as well, I can have both of them displayed at the same time, and you can see that the flow lines are simply duplicated and visualized at a more discrete level in the section, but we're showing exactly the same information. If I want to drill down and find areas of similar sorts of pressure, well, I can go and create something called an ISO surface. Those of you familiar with Creo Simulate will be familiar with creating ISO surfaces in Creo Simulate. So if I select an ISO surface and go and pick it in my results session, what I can do here is tell it the variable that I want to examine, and let's have once again a look at the pressure, and go and change the values now, so we can go and examine areas in the assembly here that have the same pressure within them. And again, if I go and turn on the streamlines at the same time, this gives us a better idea to look at the swirl of how the material is coming in, and then it's starting to feed down this vortex here. If I go to my streamline on its own, I can just leave this turned on by saying surface yes. That keeps it in perpetuity. It's going to be continually shown, and then I can come down here and I can see once again areas of similar pressure within my assembly. So I wanted to show you that live just so you get an idea of performance and how it actually integrates with Creo and how easy it is to actually set up the experiment. So let's go back now to my presentation. So the first experiment that we were going to look at I've shown live. The next few I'm going to talk through for you. So this is now looking at the external analysis, and this is looking at a drone here. So we want to go and perform an experiment on quite a detailed assembly here, and once again take note of the performance of the system as well, and how we're going to be able to analyze what is a relatively large assembly very, very quickly indeed. So once again, these 4 key areas that we need to fulfill: applying the physics, telling it which domain to apply those physics to, setting up the boundary conditions, and then examining the results. I'm now going to add fluid domain, so unlike last time when I went and created the fluid domain, I'm going to say all the components within the assembly are going to be instrumental in setting up this particular fluid domain. Now, unlike the previous one, you can see these are added to my domain model tree here. Unlike my previous experiment, which was an internal experiment, this is going to be external. By default, we say that all experiments are going to be interior, and this one is going to be exterior instead. So let's go and pick on the drop down, tell it that it's going to be exterior, and it then creates effectively the hanger into which we stick the plane. And I'm saying that I want this hanger or bounding box to be 50% bigger overall than the thing that we're going to analyze. So if the plane is 5 meters long, it means that 50% we would get 2.5 meters in front, 2.5 meters behind. If it's 2 meters tall, it means we would get 1 meter above, 1 meter below, that sort of thing. So this is creating the cells now live. There's no editing to the recording here. This is as it actually ran. So it's creating the cells, checking the faces with respect to the geometry, and then building the mesh off of those cells. Excuse me. And here we go. This is the hanger, effectively, that sits around our plane, and these are all the plane components within it. So you can see this is the mesh that's just been created in our results section of the model tree. Next thing to do is to add some boundary conditions. So on this front face here, leading into what is effectively the hanger, I'm going to assign a velocity in a similar way that we did with the cyclone model. I'm going to tell it that it has an input velocity of 268 meters a second, which equates to 600 miles an hour. So running very fast indeed. So instead of having a solid wall here, let's say that we want a specified velocity And once again, I'll do this normal to that inlet surface and give it a value of 268. I'm not electing to release particles from this front face. I'll do that in a slightly different way, and the reason for that is because if I let smoke simulation or simulation smoke come in from that front face, I'll just be overwhelmed with all these streamlines and all the flow information that I won't actually be able to see what's happening on the surfaces of the plane itself. So I'm going to select those in a slightly different way. So the remaining 6 or 5 faces of the hangar, what I did there is I said apply the same velocity going towards the rear of the plane, and now I've picked the wings and the nose cone, and those alone for releasing the smoke particles. Now I've hit the run button now without doing the meshing up front. It goes and creates it for me, and immediately we can start to take a look at the streamlines, and this is prior to the experiment actually having finished. You can see that the run button is still grayed out at the moment, and that indicates that it is still calculating. So you can see, interestingly, that there's a streamline that's actually shooting up by virtue of the fact that early on in the experiment it's looking at the propeller on the back of the drone, and that's interfering with the flow going over. So this is going to continue to refine as the experiment continues to run, and I'm just highlighting the numbers here on the model tree, and you'll notice that when I hit refresh, those numbers are changing. So it's continually refining, and also the flow lines are starting to become smoother, and they're becoming more normalized, as you would expect as the experiment progresses. So let's go and change the line thickness and the time steps for this experiment, and now we can start to see the flow lines more clearly passing over the wings. Something to note here, there are 2 different styles of wing on this drone. The one on the left is an idealized wing. The one on the right is a aerofoil section that has actually been bent around a camber line. So we're getting proper lift off the wing on the right. How much lift? Well, we can go and drill down to a more granular level here by specifying that we want to see specifically the lift on that wing. So now let's go and look at that wing in isolation, and quite clearly we can see that we have low pressure on the top and we have a high pressure on the bottom. So this wing is clearly going to be giving us some lift here. And you can see that the results that we get on the surface correlate to the results that we get from the flow lines as well. Let's go and compare and contrast now with the wing on the opposite side of the plane, and let's go and put the pressure profile on for that. And what you'll notice is, because this has not been bent around the camber line, this wing here, the aerofoil section, you can see that we get the same pressure on the compression and both the suction faces. Well, we don't actually have a compression and suction faces since it is symmetrical, so we're getting the same values on the top and bottom faces of the wing as we see it. We can go and again drill down. I want to show you how we can find even more information by using a section view here, and once again let's put the variable and the parameter that we want to examine here to pressure, and you can see that we have this symmetrical pressure around the upper and lower face of the wing on the left. Compare and contrast now to that wing on the right hand side, and you'll see that we have a low pressure on the upper side of the wing, and on the underside we have the high pressure, demonstrating quite clearly that we're going to get lift in this experiment. So if you're looking at something like not just a wing in this circumstance, maybe you're looking at something like a motorcycle that has a it's an off-road cycle that has a large mud guard on the front. Is that going to be giving you a lift problem as it's traveling forward at perhaps a motorway speed, where it's going to make the front wheel too light? And that's the sort of information you can derive from an experiment such as this. Okay, moving on to the next experiment. This is looking at the flow through an electrical enclosure over hot electrical components. So let's set this running. Now I want to tell you beforehand that I have edited this movie a little bit, because there are some components of it that I didn't want to dwell on too long. I realise that I'm limited to a certain amount of time here, so I have actually taken out a couple of bits here just to ensure that we get through the presentation on time, and I'll tell you exactly where I have made any edits. The first thing I'm doing here is specifying the fluid domain within this assembly, which is where the experiment is going to be performed. So not only do we have the fluid now, but I'm going to add the solid components. These are all the components that are inside that assembly. I'm going to add those as solid into the experiment as well. Let's tell it what physics we want to look at. So we want to look at the turbulence, the heat effect, and of course I want to examine the results, so we add the streamline in there as well. Now this is an important point. You'll notice that the materials have come through automatically. So if the materials are assigned to the components already, they will come through into the flow experiment. Now we're going to set up some boundary conditions here, and in this instance I want to say that we have a chip here that's going to have a power source of 5 watts. So you can imagine what happens when your bulb blows in your house and you go and unscrew it. It's hot to the touch, and we're doing the same thing here. We're applying a wattage to that particular chip. And now I've also set up that I want to graph the temperature of that chip as we actually go and run the experiment. So we've set up a boundary condition for the chip. We've told it it's going to emit a certain amount of heat. Next we need to set up some boundary conditions for the actual cabinet in which all of these components sit. So at the back I've said it's just going to be open, and on this front face I've said that it's going to have an outflow of 0.001 cubic meters per second. So let's generate the mesh. An important thing when you have both fluids and solids is to have this boundary mesh, the interface mesh, between the two components. And again, that has to be a very robust mesh that's going to reflect the interface between the two different materials. So let's go and pick all of those components that are involved in the interface. You can see in the model tree on the left here, it's showing the fluid, and then it has a slash, and then it shows the solid component which is interacting with that fluid. Okay, let's run the experiment now, and on the right hand side what we're looking at is the XY plot for the temperature of that chip. You can see it starts off at ambient temperature. This is in Kelvin, so it starts off at 300, races up to nearly 400, and then comes down to a steady state of something around 345. In the assembly itself, what we're looking at here is the flow of the air going through here, so the velocity of the air. You can see, as we had in the previous experiment, the button was grayed out for some time there, so even though it hadn't finished the actual calculations, we were still able to get early insight into what exactly was happening within the calculation. Okay, let's go and make some changes now to our boundary conditions, and let's go and up the flow rate through this assembly. Something I'd like to show before we do that is just the heat distribution, and drill down into this experiment a little more to show how the heat distribution is actually affecting other components on that motherboard. And you can see that the chip is actually warming up another couple of components there. We can go and again create a more discrete view of this world by going and looking at a section view through this experiment, and you see quite clearly how the air is drawing the heat out of the heatsink. Using an ISO surface, this will give us a 3D view to better enable us to visualize exactly how that temperature is being drawn out of the heatsink. Let's go and pick a different value, and there we go. You can see in a 3D view quite clearly how that heat is being drawn off the top there. So let's change the boundary conditions now and say that we want to double the capacity going through here. So from 0.001 cubic meters a second, we're now changing to 0.002. The thing to note here is, as the experiment is running, you can see how the heatsink started off really quite bright orange, bordering on red, and then it's settled down to a yellow color now, and it's almost bordering on green. The other thing to note is the XY plot. Again, we started at 300 degrees Kelvin, raced up to about 365 there, and we've now come down to a steady state of something approaching 325. So the 325 correlates directly to the color rainbow icon directly above that. So the 325 will relate to that rainbow, which relates to the heatsink itself. So you can see that we're somewhere in the middle there, around the 325. So all of this information, whether it's shown as a temperature plot on the actual components, or the temperature of the flow lines, or the temperature on the graph, we can tie all of these things together. So we get a very good insight into what exactly is happening in the experiments that we're creating. One of the things that's interesting to note here is that a lot of the flow that's going into the upper part of the electrical enclosure is very slow moving, and there's not an awful lot of flow actually in that area. Right, now me as a good old engineer, I'm thinking I would like to get more air into this enclosure. And that's the typical thing that an engineer tends to think. An analyst thinks very differently, I think, from an engineer. Engineers think bigger is better, so let's give it more air going in here. Whereas analysts, I think, tend to think a little more strategically. And this is where really we're crossing the boundaries between disciplines by enabling the engineer to have access to CFD. He is able to get a better insight into the world of the analyst and make changes in his design more analytically rather than based upon sort of empirical experimentation. So let's have a look now. And what we're doing here is introducing a couple of new slots into the bottom of this housing. And we now return to the experiment. And what's really nice about the Creo CFD product is even though we've gone and applied all of these boundary conditions and all of these domains and the different components that are going to take part in the experiment, both the solid and the fluid, we don't have to go and reconfigure that. We simply have to tell it the extent of the experiment volume, and everything else is carried over from the analysis that we created previously. So once again, we're going to plot the temperature of this chip, and what you'll notice is previously it settled down to a steady state of something around 325. In fact, what we're getting now is something approaching 330. So by putting these extra slots into the back of this electrical enclosure, we haven't actually improved the performance, we've degraded the performance, and the reason for that is the flow of the air is now passing under the heatsink and not going through the fins of the heatsink. So this is where we start to bring together the two worlds of analysis and engineering by enabling the engineer to have early insight into the world of the analyst. Instead of making assumptions, he's actually able to drive his design with clear results from the world of analysis. Okay, moving on to the final example now, I'd like to take a look at an assembly. So what's happening in this particular experiment is we're taking a pump. We are going to be passing a fluid through this pump. So instead of air, this time we're going to be changing the actual material that's involved in this experiment. And we're going to be breaking the experiment into various different components. We're going to have a fluid component coming in up to the actual blades. And then the blades are going to be revolving around inside this involute, which is going to be the third component. So let's see how we go ahead and set up this type of experiment. Once again, you can see that I'm working in the world of Creo, and to go into my flow analysis, it's simply the menu pick on the ribbon up there, and once again we're going to be fulfilling these four components of the experiment. We need to tell it what physics we want to employ, and then where we're going to be applying those physics to. So let's go and create ourselves a fluid domain. And the openings of our fluid domain are these three faces here. You can see that it's also gone and picked up the screw holes on these faces. So I want to go ahead and exclude those screw holes. The 8 from that face. And the 8 also from this end flange here. So let's remove those as well. And then go and add this fluid component to my simulation. So in the model tree you can see that I now have this new fluid part. If we turn off the CAD bodies, you can see this is simply the fluid that I'm left with. And I'm now going to chop this up into three components. I'm going to slice it away from the revolving component to start off with. So we end up with a fluid component on the left and the remaining component on the right here. This remaining component I'm now going to split again about the central axis of revolution for the blades, and let's give it a size, and we end up with a rotational and a static component for these two areas here. So now you can see in the model tree I have these three components, and those are going to be the three components that define my fluid in my experiment. I'm going to refine my minimum cell size for this because I want it to be quite accurate on the interface between the actual rotating part and the involute itself, so I've got to make that twice as accurate as the default value that we would normally use. Now this is running live, so you can see that it generates the mesh very quickly indeed. Just let it run through. So now adding the mesh, and that's it. Very quick to actually get a very accurate mesh. If I just go and show you some of the detail on this mesh, zoom in onto the edge. This is why I wanted a particularly detailed mesh here. I wanted to have a good interface between the components here. Now let's go ahead and set up my boundary conditions. The things I'm going to, the way I'm going to actually perform this experiment is, I have two ways when I do a moving experiment or a rotating experiment like this. I can actually remesh, and I can have a rotating mesh that I have to recreate for every increment that I want to run the calculations, or I can create something called a non-inertial frame. I'm just assigning the materials here and saying that this is going to be water. In this instance, I said the non-inertial frame is going to be running at 100 radians a second, and on the outlet here, I'm going to have an outlet of 1 cubic meter a second, and going in on the inlet, I'm saying that I want to have just normal atmospheric pressure. So these inertial frames, what this does is this is a great way of actually simulating a recalculated mesh without actually having to go through all of that recalculating. So it performs very quickly, very accurately, without having to go through all of that remeshing all the time. Now note that the run button is still grayed out here, so it's still calculating, yet I'm able to go down to the results section and take a look at what's happening before it's even finished the calculation. This is really important because if you're having to set up your experiment and then click the run button and wait till it's completed before you find out whether or not you've actually set up your experiment correctly, then you could waste an awful lot of time letting an experiment complete, find you've set it up incorrectly, having to reconfigure your experiment, and then go and rerun it. By getting a very early insight into exactly what's happening, we're able to establish whether or not we have set up our experiment correctly in the first place. So as I did with the other example, I'm going to continually refresh here, and we can see how those results are refining as the experiment continues to run. So let's now go and actually drill down to a component level and see what the pressure's like actually on the rotating portion of this assembly. And combine that now with the section view, and you can see that every way we go and view these results, we're always looking at the same information. We're just drilling down to a different level of abstraction, whether we're looking at an overall flow, a specific localized component, or an isolated section, and they all give the same results, it's just in a different level of detail. Let's go and create an ISO surface and find areas with similar sorts of pressures throughout this experiment. And once again, I'm going to look at the pressure for my ISO surface, and this is interesting to see how the pressure drops off for each particular blade. So it rises as it actually pushes the fluid round, and then once it's past that particular blade, the pressure drops down and then rises and drops and rises and falls for each particular blade. And here again we can just go and vary that pressure value so that we can find different ISO surfaces with different areas of different value. Okay, the variable that I'm going to take a look at this time, instead of looking at pressure, I'm going to take a look at the temperature of this particular experiment. And you can see that the extremes of this experiment are approximately 0. So the inlet and the outlet are basically the same value. I'm now going to change the rotational speed. I'm going to multiply that by 5 times, and instead of having 100 radians per second, I'm going to go to 500 radians a second. Let's go and hit the refresh button and see what impact that actually has on my experiment. And you can see that it's settling down now, and it's starting to refine the result, and we're getting something around a just under 40-degree variance in both inlet, or it's gone up to about 50 now, variance between the inlet and the exhaust temperatures here. So this is quite interesting. What you can do is you can find out very early, if you go and increase the performance of your pump, what's going to be the impact on other components within that assembly. So in the same way that we could go and increase the through flow of the experiment in the electrical enclosure, we could see what the impact would be on the cooling of the components in there. In this instance, by upping the flow rate, we can see that we're going to get a temperature gradient now far greater than we previously had, and you'd then be able to consider what the impact would be on other components in that assembly. Maybe you've got seals on the bearings that wouldn't be able to withstand that temperature gradient, and you'd have to consider using alternative components. And this is the sort of information that you can get, this early insight into the potential design problems you may encounter if you didn't have access to a tool like CFD. So we've already looked at had a package overview from Lee. Let's go and have a look at the packages that were employed in these particular examples. The first two, we were looking at the basic Creo flow analysis package. So doing just simple flow for turbulence, all you need for that is the foundation package. Looking at the other two examples, I was using functionality there that you would require the middle package for. So this is looking at things like the heat and the radiation in these particular experiments. What do you get with the premium package? Well, that gives you access to functionality that would enable you to model things like cavitation and do these sorts of experiments at the top, where you can go and look quite clearly at the result of how oil would flow around a gear pump, or at the bottom here where we're mixing different components or different materials together into a lobe pump. So that's the sort of experiment you could run with the high-end package. And that's me finished now, so just to hand you back to Lee, and thank you for your attention.
Thank you, Phil, and thank you all for watching. A link to the recording for today's session will be emailed out to you shortly. Please take a moment to connect with us via our social media channels and subscribe to our blog, and we'll keep you up to date on all the latest product enhancements from PTC and updates on our future product development webinars. Thank you again, and enjoy the rest of your day.